I'm going to try to give you a very general overview on gravitational waves from very different point of views. So not only astrophysics, but also general relativity and fundamental physics, and maybe with some bits of mathematics, because there is a connection there, which is very interesting, but I will see. This is going to be, there is no book that we're going to follow, because I want this to be as intuitive as possible. What I want you to develop a kind of intuition for what all of this is about. I mean, if I were here just to read aloud a book, there would be no point to these lectures, right? You would take the book by yourself. Anyway, so let's go for it. I'm going to start with a diagram. This is these are two axes, right? And over here, I'm going to write, this is going to be in log scale, base 10, of quantity, which I'm going to call HC. Over here, also in log 10, I'm going to show you the frequency in hertz. Okay, so first of all, what is this HC? This is important. So HC, this C over here stands for characteristic, and it is giving you a feeling for what is going on. It is a characteristic property of the wave that you are measuring. It relates the variation of the length of your detector to the length of the detector itself. So it's one quantity divided by the other one. What does this mean? This means that if you have an interferometer like LIGO or LISA or whatever, we have one mirror here. We have another mirror out there. And what we're doing over this length, L, is to measure tiny variations of that length. It's a dimensionless quantity because it's one quantity divided by the other one. And this allows you to understand what is going on the different windows of the detectors. For instance, let's have a look at my favorite one, which is LISA. Something like that, okay? Around here, this is 10 to the -5. And this should be here, should be around 0. So for these kind of values, you get, let's say, 10 to the -20 should be around here. So this is -20. And in reverse order, so increasing, we have here -15. So what does this -20 and -15 mean? This means, but let's look. I'm going to plot as well LIGO. LIGO should be around here, something like that. Okay. So LIGO, as you can see, is in this kind of regime around here in sensitivity. So what does this mean? So you know that LIGO has been measuring the coalescence of binary black holes and the spiraling of neutron stars. So LIGO has a length of what, a few kilometers, 4 kilometers. So the first gravitational wave ever discovered, which was GW, and I'm not quite sure why they picked up these two letters, 150914, I think, because I always get that this is actually a date, right? It was the 15th of September, no, the contrary, it was the 14th of September 2015 in the US way of picking up the dates, which is very confusing for me. So this first source reached us after traveling a distance of about, I think, 480 million parsecs. Just to give you an idea for how long this is, if you convert this is about over 1 billion light years. Which means that the two black holes that were spiraling and finally merged with each other, they merged when life here on Earth was starting at a cellular level. So, but going back to this delta L, in order to be able to measure these gravitational waves, the LIGO detector had to be able to measure 1,000th of the width of a proton, okay, in the 4 kilometers. This is what this plot is telling you, this kind of numbers, 10 to the minus 25, etc. So you are measuring in 4 kilometers, you are measuring tiny little fractions of a very, very, very small part of a proton. Okay, it is so amazing, this kind of tiny distances, that you actually, and that this is something that we can talk about if you want, in the mirrors over here, you care about quantum noise. So the particles in the mirrors moving around, they're going to produce some noise, and that's going to contaminate the source, and you have to take that into account. So this is kind of sensitivity that we're talking about. There are some interesting comparisons. They say that you're measuring 1,000th of the width of a proton over 4 kilometers of length, which is equivalent to changing the distance to Alpha Centauri, which is the nearest star that we know outside of the solar system, by 1 hair's width. So we're not used to this kind of precision in astronomy. In astronomy, you know that we're happy whenever we get things within 1 order of magnitude. Here we're talking about ridiculous errors. So the precision of the measurements is so small that we get to do extremely interesting measurements, but that comes at a price. It comes at a price because you must be able to be sure. So you must be sure, sorry, that your signal does not contain any kind of error exceeding the measurement that you want to do, right? This means that if, for instance, you have a binary in Lisa here, and you're trying to detect a binary, if you make a mistake in the template that you want to use to measure that binary, in the eccentricity, you make a mistake of about, say, 10 to the minus 2 or 10 to the minus 3, you have a big problem, because it is very likely that you're not going to be able to extract parameters as well, as good as you would like to. Okay, good. So let me clear this a little bit. Sorry, I'm still a bit because of this COVID. So let's go back to these detectors. I want you to think. So you can relate this frequency to masses. Okay. You can think of this as a frequency in hertz, or you can think of these three different windows. We have here, say, one window, two windows, but we have a third one, which is over here. It should be like this, which corresponds to PTAs. So this is Lisa. This is LIGO and Virgo, and over here we have the so-called PTAs. I can talk about that in a second. But what I want you to understand right now is the following. So we can divide these three windows according to different regimes. Over here in the PTA window, we're talking about black holes with masses typically larger than, say, 10 to the 7 solar masses. In the LISA window, we care about black holes or systems of gravitational waves with masses typically between, say, 10 to the 7 and down to, it depends on a lot of things, but these are the typical numbers. It depends on the distance to the source, etc. But typically, we're talking about 10 to the 7 and, say, 10 to the 3. And in LIGO and Virgo, we're talking about black holes or systems with masses of at most 10 to the 3, again, depending on the distance, and down, as you know, to the mass of a neutron star or whatever, 1 solar mass. So as you can see, I probably have noticed this already, but in case you didn't, I'm going to stress it out. As you move to the right, you go down in mass. So on the left, we have the very massive things, the real supermassive black holes, 10 to the 8, 10 to the 9 solar masses. In this in-between regime here, between 10 to, say, 10 to minus 5 and 1 hertz, we're talking about masses of 10 million solar masses and 1,000 million masses. Sorry, 1,000 masses. And in the LIGO and Virgo regime, we're talking about systems with masses of between 1,000 and 1. Now, this is a very interesting way of distinguishing how we look at sources. Because over here in the LISA window, we're talking about black holes, for instance, black holes with masses like the one we very likely have in our Milky Way. You know that when we look at the center of our galactic center, which is a redundancy, but anyway, when we look at the center of our galaxy, we see something which should be a black hole with a mass of 4.3 10 to the 6 solar masses. So 4.3 million solar masses at a distance of 8.3 kiloparsecs from us. So it turns out that the Milky Way is a very representative galaxy. So there are millions and millions of galaxies like our Milky Way, and that's very good because we have a lot of potential sources of gravitational waves that LISA or any detector similar to LISA is going to be able to look at. Now, There is another interesting correlation that you can get out of this diagram. The same way that moving from the left to the right over here implies moving from more massive to less massive, moving from the left to the right over here means spending less and less time in the band of the detector. Why is that? That's because the characteristic time scale, and I will describe all of this, I will introduce all of this in detail about the course. The characteristic gravitational time scale is proportional to the semi-major axis of the binary to the power 4. Now, there are many different ways of producing gravitational waves, but I'm going to be focusing on binaries. There are, so some people talk about cosmic strings. Well, I don't know anything about cosmic strings, and I don't think that many people do, which is why I'm going to just stick to facts that I know. And I know that binaries exist. So I'm going to be focusing for these lectures 100% on binaries of objects. And it turns out that the gravitational wave timescale for one of these binaries is proportional to their semi-major axis to the power 4, plus or times all the things, all the factors, which I am not showing now. Now, why is this important? This is important because the semi-major axis over time is going to evolve like this. So it's basically not going to change for depending on the system that you're talking about. But for instance, we could be talking about a very small compact object, say, don't know, a neutron star or a white dwarf or a very small black hole with mass of 10 solar masses, say, flying around a supermassive black hole with a mass of 10 to the 6 solar masses. So for a very long time, the distance, so this image axis is a kind of distance between these two objects, is not going to change very much at all, actually for up to millions of years, until the thing starts to emit gravitational radiation, and then there's a kind of a snowball effect. If there's well, there's a power over there, so that you just go like this. So for millions of years, this is time, right? And for millions of years, you basically see no change in the separation of the binary until you reach the gravitational wave dominated regime. And in a very short time scale, you have extreme changes in the semi-major axis. And actually, this is for anyone out there who has been trying to plot this kind of graphics, the evolution of the semi-major axis as a function of time, you will know that this is actually a problem, because plotting programs usually they go and plot this with dots, and they are stupid enough to use a lot of dots here and to run out of memory, in particular if you're using Python. I don't like Python, sorry. And then you have I know that some of you are going to protest, but I don't care. And over here you have a sudden change, and then you get a few points, and that's going to, this is actually a problem for the plotting program. But anyway, this is just kind of a fun fact about what I am describing. Anyway, let's go back to this. So for these lectures, I'm going to be focusing, as I said before, on binaries. And I'm going to be focusing on this particular region of phase space. Why is that? Well, first of all, because I've been working for this experiment for the last, I don't know, 17 years of my life. And also because, and I am not biased, because this is where you probably can get most science from. There are many different sources that you get in LISA, and the interesting thing, going back to the time scales, is that here we're looking at extremely long time scales. In the window of LISA, we're typically looking at time scales of months, if not years of data. And in the window of LIGO and Virgo, we are limited to typically nanoseconds. Okay. So over here, you get a width of data. So a very short stream of data. If you're talking about neutron stars, probably you can get up to 1 minute of data. But over here, LISA window, we're talking again about months, if not years of data. And the first reaction is to think, oh, that's amazing. That's very, very nice, right? Well, yes and no. Yes and no, because the point is that, for instance, for the kind of systems that I was talking about before, you have a small black hole, sorry, a supermassive black hole of, say, a mass of 10 to the 6 solar masses, and a small black hole moving around it. So for this kind of systems, you have a problem, because this mass, the mass of the small object, let's say that it's a mass of 10 solar masses, you have a mass ratio of 10 to the 6 divided by 10. This is the 10 to the 5, right? And these mass ratios, this kind of mass ratios represent a very big problem, because we do not know how to solve Einstein's field equations with these mass ratios. So we do not know how to produce, even with supercomputers, this kind of motion of distance. So how did we actually make the first measurements of gravitational waves? Well, in the case of LIGO and Virgo, the first source that they ever measured, which is this one over here, the system was composed of two black holes of masses about 40 solar masses. So the mass ratio was basically 1. And for this kind of mass ratios, we're happy. We can solve Einstein's field equations, although it took us many decades to do that. So if you look at the evolution of one of these systems, like the one that was shown to you before, the gravitational waveform is going to, so one of the polarizations is going to look a little bit like this: jup, 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 and every one of these peaks corresponds to the moment in which this small black hole is very close to the supermassive black hole. So when you are at the very center of the system, right? So for one of the systems that I was saying before, for the LISA window, we're going to be looking at them evolving for months, if not years, which means that we have months, if not years, of this kind of data. Now, in the case of LIGO and Virgo, we're looking at one of these peaks. So we're talking about nanoseconds sorry, I have to check because I don't remember. But anyway, we're looking at a very short time intervals in the case. And that was already a big problem. That was a big problem because for many decades, as I was saying before, we never, so for a very long time, we are not able to solve Einstein's field equations, not even for one single black hole, not even with supercomputers. So with supercomputers, they tried. I didn't do anything. I'm talking plural. I don't know why, but they tried to solve one black hole, and for many years the codes were just crashing because they were not able to even integrate one single isolated black hole. When they were able to do that, they tried to go to a binary, and they were not able to manage half an orbit. All of the codes were just crashing. And this is an advantage of being in competition, because there were many different groups working on this. There were a few of them in the US, a few of them in Europe. I'm not sure about China, actually. I know that China is moving nowadays a lot in that direction. But back in the days, I don't remember. But the point is that so for many years they were not able to integrate half an orbit because the codes were unstable. Until in 2005, a few decades later, a guy called Franz Pretorius came up with not a trick, but a way of looking to the problem which was slightly different. Now, thanks to this idea, he was able to solve the problem. He actually wrote his own code. And at the beginning, people, I've been told, because I was not there, but at the beginning, people were laughing at him and they did not believe him. He was actually applying for jobs here and there. And he was claiming to have solved the true body problem in numerical relativity. And they didn't believe him until these different groups, which were competing among each other, implemented the same, in quotation marks, trick, because it's not a trick. And it turned out that all of those codes, which were very different, all of them worked. And that was a real achievement. Why? Because, you have different groups, group A, group B, and group C competing with each other, with tens and tens of people working on a problem. And each one of them wrote their own code, which was completely different. Of course, all of them were solving Einstein's field equations, but they were solving it in a numerical way, which was very different from each other. And with the new idea of Franz, all of them, A, B, and C, were able to solve the two-body problem from a numerical point of view, which is why some people call the golden year of numerical relativity, 2005. So it took us decades to solve one of these small peaks. But we're not talking now about one peak. We're talking about 100,000 of them, because this thing, the system that I was describing before, so you have one supermassive black hole over here, and you have a small black hole moving around it like this. So this system is going to describe a number of cycles which is proportional to the mass ratio. So if your mass ratio is 10 to the 5, you are going to describe 10 to the 5, so 100,000 of these cycles until the small black hole plunges through the event horizon of the supermassive black hole. So this is amazing because you can do incredible physics with this kind of systems, but this is also extremely challenging because, again, we needed decades to solve one of those peaks. But we're not talking about one peak, we're talking about 100,000 of them from one system. So the point is that right now we do not know how to do this. This is not quite true. There are ways around. But the truth is that right now nobody can solve the two-body problem in numerical relativity at this kind of mass ratios. Now, there is something interesting that I want to mention before I move on, and it's the following. It is the intermediate mass regime, so mass ratios of, say, 10 to the 5, 10 to the 4, 10 to the 3, and 10 to the 2, which are a pain and difficult to address. If we move further down, so if we go down to mass ratios of 10 and 1, we're fine, okay, nowadays. And actually, even somebody addressed this mass ratio of 100, but anyway, I don't think that was very useful. But what happens when you move in a different direction? So if you go to mass ratios in which this particle here, so the small object, becomes lighter and lighter, you will have mass ratios of 10 to the 7, 10 to the 8, 10 to the 9, etc. So this small particle over here becomes more and more a kind of a test particle, like a speck of dust, if you want. And at these mass ratios, back reaction makes your life easy. Why? Because on this test particle regime, the orbit of the second compact object becomes more and more like a simple and easy geodesic. So the lighter and lighter it is, the closer and closer we get to the test particle regime, the more and more it resembles a geodesic. And geodesics are nice because they're easy and we're able to solve them, at least in the Schwarzschild case. We can do that. In the Kerr case, well, the history is completely different, but it would be, it's going to be easier. So I can go now for a detailed mathematical description of the geodesics, but I'm not going to do this today. I'm going to do that the next day. First of all, I want you to have in mind the different sources that we're going to be looking at. Okay, so again, this is characteristic amplitude. Remember how much you can stretch or compress your detector's arm divided by the length of those arms as a function of the frequency in hertz. And over here, we have my favorite detector, which is Lisa. So anything above that sensitivity window, in principle, is measurable. And I say in principle because contrary to electromagnetic detectors, and probably some of you are used to talking in terms of sensitivity windows, sensitivity curves. So you know that, for instance, this event here has a signal-to-noise ratio, which is proportional to the height above the curve, right? Well, this is not the case in gravitational wave astronomy. The signal-to-noise ratio is something different. It is the height above the curve, but it is also related to the surface below the curve over the observational time that you have been looking at. So the signal-to-noise ratio is not going to be just the height, it's going to be also related to, it's not the area, but it is related to the area that you describe. So you start observing the system here, and in say, let's say 1 year of time, this is 1 year, it has moved from here to here, right? So you have this area below the curve. So the signal-to-noise ratio is going to be related to that. Okay. But before talking about these things, let's go back to the sources. So on the one hand, we're going to be looking at binaries of supermassive black holes. There are different ways, but anyway, I don't want to confuse you now. There are different ways of looking at the waveform, right? Waveform is a way to describe the gravitational wave, but it's not the only way to describe it. And in the frequency domain, supermassive black holes probably go like this. Okay. Say this is a typical binary of two supermassive black holes of masses probably, I don't know, 10 to the 5 solar masses plus 10 to the 5 solar masses at a redshift of something, I don't know, 1, for instance. So in about a few months, it will enter the gravitational wave detector, and it will merge over here. So in that period of time, you have this data at your in your data stream. Why is this interesting? This is interesting because, first of all, as I will explain, we still do not have a robust, I don't want to say proof, because in physics we do not have proofs, but we don't have a strong or a robust indication that black holes exist in nature. We have a hint they should exist, like for instance, of course, LIGO and Virgo detection. The second strongest one, in my point of view, is the kind of measurements that they have been doing at our galactic center around a radio source called Sagittarius A star with the so-called S stars. I will also talk about this later. And also with the Event Horizon Telescope, you see something with, they call it a shadow. I don't like that name, but anyway, which well, looks like a star, right? So we have some indications that black holes should exist in nature, but we don't have a compelling and strong evidence that this is the case. Well, with LISA and the gravitational waves, this is going to change. Now, you might ask the question, why not with LIGO? You can ask the question. I'm not going to answer the question today, but I will answer it. With LIGO, with LIGO and Virgo, we're not in the position of saying this observation has been a black hole and nothing else but a black hole, unless we're extremely lucky, and I will give you details. But with Lisa, we will do this on basically, a daily basis. I don't know, depends on the event rate. But we will do that with every single detection that we do. That's been interesting because black holes are very interesting. We don't still understand gravity, and the way to study gravity is are black holes. So that's one thing from a fundamental point of view, from the point of view of fundamental physics, massive, because with these mass ratios 10 to the 5, with this mass is 10 to the 5 or 10 to the 6, 10 to the 7 maybe, I feel a bit uncomfortable talking about supermassive black holes. These are very massive black holes, but that black holes can have up to a few 10 to the 10 solar masses. So these black holes over here are like lightweight supermassive black holes. In any case, they are very interesting because we don't know why, but when you look at a galaxy, and a galaxy is something huge, this thing here is my version of a galaxy. A galaxy has a width of what? A few tens of kiloparsecs, which means 10 times 1,000 parsecs, right? And a black hole with a mass, so let's say that this thing here is a black hole. The spatial radius of a black hole with a mass of 10 to the 6 solar masses is 10 to the -7 parsecs. I think this is correct. Okay, so the typical size of a black hole with a mass such that we are going to be able to look at it with Vista is 10 to the -7 parsecs, right? So from 10 to the -7 to 10 to the 1, 2, 3, 4 parsecs, there are 11 orders of magnitude of difference. Okay, so even if the name sounds very intimidating, supermassive black hole, right? The fact is that these supermassive things are little tiny things from the point of view of a galaxy. They're microscopic things, right? But we don't know why. But the truth is that this very small thing is linked to this huge thing, which does not make sense. It's like saying that, some bacteria, or one of them in your body, has an existence and evolution that is linked to your own life. And it doesn't make sense. It cannot be, but it is like this. But we don't know why. So by looking at the systems that are exactly the systems that we're interested on, 10 to the 6, 10 to the 7 solar mass black holes, we're going to get information about their host galaxies. And maybe we will finally understand why the evolution of these tiny little things is linked to the evolution of this huge monster-like galaxy. This is so because when we look at the mass of the black hole and some properties of the host galaxy, we see correlations. And of course, a correlation does not imply a causation, but it is you know, drawing our attention. Actually, it is very easy to get lost in details here. But okay, let me back up, because I'm probably confusing you. Okay, let's say this is the velocity dispersion of the host galaxy in kilometers per second. Kilometers per second. So when we look at data, we see something like this. Of course, with some scattering, because we're talking about astrophysics. But what we see is that this part of phase space and this region of phase space, they're empty. We don't have data over there. We also see something interesting. If we go in this direction, so if we go down in masses, we have less and less data. Why is that? Well, there are two possibilities. One possibility is that God or Allah or whoever, divinity, is playing a very, very nasty joke on us. Or the second, more likely possibility is that we have an observational bias here. Okay? But in any case, we observe these kind of things, and we don't know why. It's not only with the velocity dispersion, it's also with other things, for instance, the luminosity of the bulbs, although the correlation is not as tight as the previous one, and other quantities. For instance, a very interesting one they want to mention is the following. The mass of the black hole, again, this is the mass of the black hole, correlates with the number of globular clusters in the host galaxy. And why is that? Well, we don't know. So the correlation is, well, yes, has a lot of scatter, but when you go up to higher masses, if I don't remember bad, the correlation becomes better. So there is a correlation. So why should that happen? Why should that happen? If you look at our galaxy, this is our galaxy, kind of, and this is the galactic center. Above and below the galactic plane, we observe these stellar aggregations of many stars. The huge distances from the galactic center. Remember, the black hole is a small, tiny thing over there. It's like a small dust speck over there. So this is the black hole, with a size, remember, of 10 to the -7 parsecs. And at very long distances from the galactic center, at tens of parsecs, that are 30, 40, 50 kiloparsecs, we observe globular clusters. A globular cluster is just an association of many stars. Association of many stars as a system which is gravitating on itself and is constantly moving. But anyway, you typically find of the order of 10 to the 6 stars in this ball here and here. So our Milky Way has about, if I don't remember, 115 probably globular clusters. Okay, so for whatever reason, the number of globular clusters of the host galaxy correlates with the mass of this supermassive black hole, which again is a small little thing, very far away from those globular clusters. It has no effect beyond a distance of, say, 1 to 3 parsecs in the case of our Milky Way. If you move further from like 3 parsecs away from the supermassive black hole, you do not feel it, you don't feel its gravity anymore. And we're talking about distances of 30 and 50,000 parsecs. And for some reason, the number of these objects is correlating with the mass of that little thing. Why? We don't know. So by observing these kind of binaries, the little small things that I was talking about, it is very likely that we will be able in the position of retrieving information about all of these mysteries that we don't know anything about. So this is one source, binaries of supermassive black holes. Now, there is another source, which is my favorite source, which is the inspiral of a very small compact object onto one of these supermassive black holes. And this typically looks like this. Okay. So you have a system of, let's choose as compact object. So our compact object is going to be a small black hole with a mass of 10 solar masses. It's going to be our default system. And the supermassive black hole, is going to have a mass of 10 to the 6 solar masses. I am picking these masses because, first of all, they are representative for the Milky Way. And secondly, because these kind of masses, well, this is very sensitive to them. So why are these objects or systems interesting? Well, they're interesting because of what I was explaining before. First of all, if you know that in the case of our Milky Way, this is again our Milky Way, and this is the galactic center, right? This is not a black hole, this is the galactic center. So we have ways like between the outer skirt of the galaxy and the galactic center, way around here. So this is us. And we move around the galactic center in a kind of, well, this is a kind of a very circular trajectory, like this. But this is a Keplerian orbit. And it is very nice that it is a Keplerian orbit, because otherwise we would have problems. And there is something interesting about this region of the galaxy, because if you look at, I don't know, say, no, so let's imagine that this is our solar system. So this is the sun, and we have the planets here, right? So, of course, as they say, this is not to scale. The dimensions are completely wrong, but anyway. So if you look at 1 cube of length 1 parsec, right, in all directions, on average, in that cube, we have about 0.05 solar masses per cubic parsec. So we have 1 parsec here, and of course another parsec in the third direction. So in 1 cube of length 1 parsec, we have about 10 to the -2 suns, like the star in our galactic system, solar system, right? Now, if we move over here to the galactic center in exactly the same volume of 1 parsec of size, instead of having 10 to the -2 solar masses per cubic parsec, we have up to 10 to the 8 solar masses per cubic parsec. Typically 10 to the 6, 10 to the 7, but up to 10 to the 8 solar masses per cubic parsec. So this is an extremely crowded place in the galaxy. It's actually not in the galaxy, the whole universe. If our solar system was here, we would have a lot of problems. Why? Because if this is our sun, at any given point in a relatively short time scale, another sun would fly by and completely disrupt the planets, and we would lose our sun. But so I was talking about this because I was mentioning that our solar system is just going around, I don't remember which way, I don't know, this way or that way, but anyway, it's going around the sun in a Keplerian orbit, right? And it's a very stable. Now, if you take a supermassive black hole and a small compact object, the thing is not going to be on a Keplerian orbit, which would be the system. So this is the supermassive black hole. And over here we have a small black hole. This is not going to be the case because of general relativity. First of all, we have a constant emission of gravitational waves. In particular, here at pericenter, we have a lot of emission of gravitational radiation. And emitting gravitational radiation means that the system is losing energy. If you have a binary and the binary loses energy, what happens is that the symmetry axis, which initially was that, will become smaller and smaller and smaller over time. Okay, this is the first thing. So the two compact objects, the supermassive black hole and the black hole, are getting closer and closer to each other. This is the first thing. The second thing is that the system is going to precess. We know that this is a relativistic effect. We know that Mercury is precessing around the sun. And what people don't usually know is that about 98% that precession is Newtonian. And this was actually the big achievement of special or restricted relativity. It managed to explain that missing 2%. Okay, but in any case, Mercury is precessing, and we can explain that with Newtonian physics and the help of special relativity. At this kind of length, because we're talking about milliparsecs, 10 to the minus 3 parsecs usually, and with this kind of masses, the small black hole is going to be moving at a relative speed of about, I don't know, 20 to 40% the speed of light around the supermassive black hole. And that's going to induce a very strong relativistic precession on the system, meaning that when the black hole moves around the supermassive black hole, it will get to up pericenter, and when it moves back, it will not reach the same pericenter, it will deviate and reach a different one. This is called precession, right? And again, etc. But we have said that the system is losing energy, and if it's losing energy, the symmetry axis is going to become smaller over time. So this is going to go like this. It's going to become smaller, smaller. I am exaggerating the effect because I told you this takes about 10 to the 5 orbits. We have only, say, 10 of them over here. I will go like this. But there is another interesting effect, because if now we're going to look at the system edge on. So this is a supermassive black hole, and this is the small black hole. if the central supermassive black hole is spinning, so if it's a curved black hole, then there is something very interesting happening. The plane of the orbit will basculate, meaning that there is a kind of, there is a frame drag effect, which means that space-time very close to the supermassive black hole will be dragged along the spin. Now, if this means the following, if the small compact object, if the small black hole is here, and the supermassive black hole is here, and this is the initial plane of the orbit, after some time, the plane of the orbit will have changed very close to the supermassive black hole, so that it will look like this. When this black hole gets closer and closer to the supermassive black hole, what it is going to have to do is to follow the plane of the orbit, which means that instead of following this orbit over here, it's going to go in this direction with some inclination. So the plane of the orbit is going to change. So all in all, we have a supermassive black hole over here, and we have a small black hole which is, flying around the supermassive black hole. It is precessing. The symmetry axis is becoming smaller and smaller over time, and the plane of the orbit is going to change as well over time. It will change over time. So we have a number of, if you want, gravitational wave bursts of about 10 to the 5. So we have about 100,000 bursts of gravitational radiation around the system. And you can actually prove mathematically that that system is going to fill up a torus, which is kind of a donut, around the supermassive black hole. Okay. So this means that the small black hole, as it gets closer and closer and closer to the supermassive black hole, is going to explore not every, but 100,000 points within the volume of this torus, which is, embracing or englobing, I don't know how to say that, the supermassive black hole. Why is this interesting? This is interesting because these 10 to the 5 bursts are something like a snapshot, if you want, a photograph, a picture of a space-time in the very strong regime. So you get to study the geometry of space-time around a supermassive black hole, which is something unique, something that we cannot do with any other mission ever thought of or even conceived by mankind. So you can study what space and time, looks like around the supermassive black hole. And it is very likely, because there is something called the theorem of Gauss-Bonnet, that you can relate this geometry to the topology of that space-time, at least in 2 dimensions. And there are extensions to 4 dimensions with Chern-Simons, etc. But anyway, I don't want to talk about this today. I was just giving you some motivation for why this is interesting. So this is the third source that Lisa is going to be looking at. The fourth source is going to be, and with this I will finish this long speech, it's going to be thousands, if not millions of sources which are compact binaries in our own Milky Way. And they are populating phase space around here. These are, in principle, white dwarf binaries. And there are so many of them, again, thousands at least, that people in the past used to call them a foreground noise. So each of these sources would be, a discovery by LIGO Virgo these days. But because there are so many of them, and actually we have guaranteed sources, we know that these sources are going to be emitting gravitational waves in the LISA bandwidth when we launch LISA. Some people in the past used to call them noise, because if you remember this distance that I was talking about just now, these spirals, this kind of systems, they are exactly around here. So we have to find a way to be able to clean, in quotation marks, all of the sources to retrieve the red curve, because that red curve is very interesting. Yes, just one little thing, and then I will be done for today. So again, if you look at this thing over here, what you have is many different sources. This is just a zoom, if you want, of what I just drew. And this one here corresponds to a binary of 2 white dwarfs. But these 2 white dwarfs are so far away from each other that even though they are emitting gravitational waves all the time, it's going to take them millions and millions of years to merge. So since we are human beings and we die after 100 years, from our point of view, this system is not changing at all. This is the same thing with constellations, right? If you look up in the sky and you look at a constellation, that constellation is fixed for us because we don't live much. Even 1,000 years before, when the Greeks were looking around, those constellations were on basically the same places as they are today. So from our point of view, this system is not changing over time, which is why we call it monochromatic, which means that one point over here is emitting at a fixed frequency. So you have one system, for instance, this one emitting at a given frequency, like a 2. But this one over here is going to be emitting at a higher frequency, 2. And this one is going to be emitting at a lower frequency, 2. But you have thousands of them. Now imagine putting together all of these sounds that I produce in a very steely way, thousands of them, and playing that music, not actually noise, at the same time. That's going to be, polluting the data stream. And even though each one of them individually represents a source of gravitational waves, and therefore it is an interesting one, it might be hiding or might be, polluting other sources which might be more interesting, like these very long inspirals that I was talking about before. Okay, so I'm going to stop here this first introduction, and now I'm going to ask